And but we have a large range of the electromagnetic spectrum, include of microwave or infrared. And but we are using for in our facility, we are focused on this high energy part, which contain mainly for UV or X-ray, mainly is X-ray. And but why we need to introduce all this? Because first thing that we are focusing on X-ray, but the property, because it's from the same fundamental things, so the electromagnetic, we can think about what the invisible light have. We have the same properties of X-ray. So this guy, if we want to introduce for X-ray, we need to show this guy first, the Rinjin, and he earned the Nobel Prize in 1901. And his main finding is for finding for X-ray. And why is called X-ray? Because when that moment, people are mainly using for lots of radiation, like particles, like alpha or beta particles. And in the meantime, I think I can stay here. In the meantime, and he found that a new radiation that happened in the vertical direction, and he didn't know what the radiation is, so he called X-ray. And why? And until now, we still call X-ray for in our moment. And as I state that the X-ray have the same property of the light. So what's the light property in our data? We have maybe the rainbow, the refraction, and the mirror image. So it's the reflection, or the sky color is the scattering. So in X-ray, we also have these properties, include elastic scattering or inelastic scattering, and more we have the photoelectron absorption. So we are now working in the single-cell radiation center, which is mainly using for X-ray, and why we have heard about X-ray in our data as well, especially maybe you go to the dentist, now everybody using an X-ray to scan your teeth. And also, you are, if you go to hospital, sometimes we do the X-ray image, but what's the difference in our X-ray in synchrotron? Because daily life X-ray, maybe the spots will be around this intensity, but we're using for the synchrotron radiation produced X-ray with the intensity will be very higher than what we have in our daily life. But maybe you know, maybe you don't know, but X-ray is still a dangerous radiation. So we need, in our data, we don't need such high intensity of X-ray. But in our research, we are scanning for our sample. So scanning our sample, we didn't need to really care about the damage of the X-ray. But we need to get good enough signal. So that's why we need a very high intensity of X-ray. And the single-cell radiation X-ray include high intensity and the continuous spectrum and the excellent parameter, like maybe blah blah blah. They have lots of benefit of it, but mainly you can image like we are scanning by using a laser. We get a really high intense and a very good colorimeter. That's why we are using the laser like this. We need to point out very well in our scanning. So this is our facility like, and in the beginning we need to have the electron out. Oh, sorry, I mentioned. But how we produce for the X-ray is we using the electron to change the direction of the electron, and then we will have the X-ray along the tangent direction of the of the electron. That's how we produce of the X-ray in synchrotron. So in the whole facility, first we need to inject electron in our ring, and we need to accelerate the electron near the light speed, and then inject into the storage ring, and then this part is the magnet that changes the direction of the electron that we can produce of the X-ray, and inject the X-ray into our inline end station, experiment end station here. And mainly we are working is not, for me, it's not working in this part. This is only our interviews, but we are mainly focused on how we using for this X-ray. So our work is mainly for the end station here. And in world, we have not only one synchrotron facility in our world, but we are only one facility in Taiwan. And we have plenty of the synchrotron facility, and in East Asia, maybe the famous one is the Spring A in Japan, and we have ESR in Europe, but as you can see that there are plenty of facility in Europe. Almost every country they have one synchrotron facility in Europe, and also there are some of the facilities like ALS or Argonne in the US. So we have a lot of synchrotron radiation research now for X-ray in around the world, and this is how we look like our facility. And we have two rings now. One is called Jrhxxhx, is Taiwan light source, and another one is the Taiwan photon source. Taiwan light source has been built around 30 years or more, and 35 years. So, but they will be shut down in recent year. But mainly we are focusing our TPS now is only 10 years starting using. And what technique we have in the TPS, we are mainly can distinguish as three parts. One is image part, and one is for the scattering diffraction, and one is for spectroscopy. And if you go to another synchrotron facility in the world, they always have these three parts of the techniques. And so now we are finished of the use of what synchrotron facility like, and we will focus on what the technique we can use in our synchrotron. So if we instant one X-ray into our sample, and as I just mentioned, we have the elastic scattering and also the spectroscopy. And elastic scattering is no exchange of the energy, so maybe not many. So mainly we are focusing on the crystal structure and include XRD or small angle XRD, small angle scattering. And the spectroscopy mainly is for the exchange of energy, so we are mainly focusing on how to analyze for the electron speed structure. So we starting from the elastic scattering. What is elastic scattering happen? Is the one light, as the scattering we have in daylight, one light when we hit our sample, and we will have a different scattering pattern. This is XRT, basic principle of XRT, and we will see different pattern, like a slice experiment, double slice experiment. So, but now our slide is from the crystal distance, like the distance of two atoms. So we will see the scattering from the distance of the atoms. So we will see the pattern. And mainly we are using for the first one is X-ray diffraction, like our X-ray instant to our sample. and we will see the hot spot pattern or ring pattern in our detector. And we interval for this pattern, we will see a pattern like this. And what we can get from the diffraction is, as I mentioned, we will get the crystal structure in our sample, like the unit cell displacing, or what is the atoms location in a crystal. And we also have, I always okay, and also we have small angle X-ray scattering and wide angle X-ray scattering, which will mainly focus on the nanostructure of our sample. If we arrangement, what we are seeing for XRD, we are mainly focusing on the atoms arrangement, assembling or order of the atoms. But if we are considering of the order of the molecule, like the two nanoparticles or plenty of compounds, we will mainly using for the SARS. It's a small angle X-ray scattering, and this is the introduce of the X-ray scattering. And what we are mainly using is for the we scanning for the lithium battery. We want to see what is when we do the charge discharge process, what's the phase transfer, what's the crystal change during the charge discharge process. And when we using different charge rate, we can see that the different phase will form during the charge process, and then we can see the time scale and also for the what's